Welcome MEEN210 students. In this third video I will be explaining the basic assembly procedure to produce the assembly that you see here on my screen, which is the wheel and bracket assembly of the parts that you created last week. So this assembly shows multiple components. Let me start by changing their colors a little bit so they can be easily identified. Let's make this one blue, make the pin yellow, and make the wheel green. Okay, so I just changed the color. I changed the color of colors of the parts so you can easily distinguish between them. We have three components: the wheel bracket, the wheel itself, the pin that connects the wheel to the bracket, and finally these four bolts that we will import from the design library. Let me walk you through the process of building this assembly. But before that, let's talk a little bit about assemblies in SolidWorks. So first of all, to start a new assembly file, it's a straightforward process similar to starting any other files, any other new file, by selecting the new file from the top menu, and then from the new SolidWorks document menu, select the assembly. Either double click on assembly or select assembly and then OK. This will open a new assembly workspace for you, and of course it starts blank and it begins by showing you the begin assembly menu. In this menu, it's waiting for you to select the components or the parts that you will include in your assembly. If you have parts that are already open in SolidWorks, you will see them listed here in the Open Documents window. If not, you can simply click Browse and then locate your files on your computer and simply select them to be placed inside the assembly. This is one way to bring parts inside your assembly. Another way would be opening the File Explorer and open the folder of your assembly components, like so, and you can simply drag and drop the part inside the assembly. But of course you need to exit the Begin Assembly menu. And if you want to import multiple parts at the same time, you can simply press Control, select all the parts that you want from the folder, and drag and drop them all inside the assembly workspace. So let's do that. I will open the folder, I will pick the three components that I want, and I'll simply drag and drop them here. You see, now I have the three parts in space. Let me go back and close the other assembly that was open. Oops, sorry. Here we go. So here are the three parts. Let me change their colors so they are clearer. Here's blue, and the wheel, let's make it, yeah, this color is good. Okay, here are the three parts in space. Type. What I want you to note is that the user interface is almost identical to the part modeling section that we completed. The main difference would be in the tabs. So the tabs up here are slightly different. We don't see the features tab, for example, anymore, but instead we have the assembly tab with a new set of icons that are more relevant to working with assemblies. We have the sketch, layout, markup, and evaluate, which we will be using many times. Other than that, you still have the design tree in the same location. You have the toolbars, sorry, the command managers there, the heads-up displays there, your work area is still there, and the toolbar with units and information. Everything is still in place. Okay. The other thing that you need to note is within the design tree. So you see that the design tree is almost identical to the parts design tree, but instead of features, you now see the list of components or parts. So each one of those lines represents one of the parts or one of the components inside your assembly. It's not a feature anymore. But you can still treat them somehow similar to the way we treated features in parts, which means that you can hide some of them, you can delete any of them, and you can also go back and open each individual one, for example, if you want to make any changes, or you can edit them within the assembly, similar to the way we edit sketches or features inside the parts. The most important thing that you need to remember that has to do with parts inside assemblies is that the first component or the first part that you insert into an assembly by default gets fixed in space, and it's usually the first one here in the design tree, and it's superseded by a letter F between brackets. You'll find here the letter F before its name. This indicates that this part is fixed in space. What do I mean by fixed? If you try to click and drag it, it will tell you that this component is fixed and it cannot be moved. But if we try with the other ones, you see that the other ones are free to move, free to rotate, or float around, except that one. Okay? Why is this? The main reason behind it is that usually when you begin a new assembly, you usually place the first component that will not usually be a moving part. Then you start importing the other components that will be assembled to that main part, which is usually fixed. But again, in many cases, you might need all your parts to be moving, which is a valid thing. And the way to do this is simply by selecting the fixed part, right click on its name in the design tree, and select float from the menu. Now you will see that the letter F disappears and your part is free to move around the workspace. Okay, so please, this is very important, because many students, when they are learning assemblies for the first time, they get confused and frustrated because one of the parts doesn't move. Whenever you try to apply any mate or any relation, it doesn't move at all, and it causes a lot of conflicts and errors. And the only reason behind these is that they forgot to make the part floating. Okay. The next thing you need to know is the following. The way that we assemble the parts together is very similar to the way that you would assemble the same parts in the physical world. If you can imagine holding all three parts in your hand, and you try to think of the sequence of assembling them together, you will find that whatever you're going to do physically will be exactly similar to what you will do inside SolidWorks, with some slight differences, of course, but the reasoning and the sequence will be almost the same. And usually this will be the same way whenever you design something that will be manufactured. So if you're designing something that you will build as a prototype for your project, for example, at some point you will need to manufacture some parts, regardless of the manufacturing method, whether 3D printing, additive manufacturing, or regular machining or whatever. So some parts will have to be made out physically, and those parts will need to be assembled together somehow. Okay, you will need to consider in your design how you are planning to assemble them together. Okay, let's start thinking about our design. So what I need to do, the first thing that I need to do, I need to place the wheel bracket somewhere. Okay, at the center of the assembly workspace. So the assembly workspace has an origin point, which we can see here, and this origin point that has the coordinates of x, y, z as zeros, like we all know. So let me bring those somewhere close to the origin point. And you will also see that we have the familiar orthogonal planes. It's okay. Here we can visualize the three planes: front, left, and right. Front, top, and right. Sorry. Okay, so here's what I need to do. I need to place this bracket. I want it here to sit on the top plane. Then I need the front plane to pass through the center of the longest side of the bracket, and I need the right plane to pass along the center of the short side of the bracket. How can we do this? By adding some relations which are very similar to the sketch relations that you are used to in sketching. So, but in assemblies they are called mates, and they can be accessed through this command up here, which is called mate. So if you select mate, you will see that you have very familiar icons with very familiar names: coincident, parallel, perpendicular, tangent, concentric, lock, distance, and angle mates. So these are the types of the standard mates that you can apply to parts to assemble them together. How would I know which type of mate to use? In many cases, it's intuitive. It's very easy to know what exactly you want to achieve. So, for example, if you want to place two things on each other, you use a coincident mate. If you want to keep two faces parallel to each other, you will use the parallel mate. If you want them perpendicular, it will be perpendicular. If you want them tangent, it will be similar, and so on. If you want to place a face or a part at a specific distance from another face, then you'll use a distance mate. Or if you want to place a face at a specific angle to another face, then you will use an angle mate. So you see it's how intuitive it is. Okay, let's try to mate this to the planes. So I need to create relations, assembly relations between the wheel bracket and those three planes. So the first thing I need to do, I need to make this bottom face, click to select, sit on the top plane. So I'll select the bottom face of the bracket and I will select the top plane. So if you notice what happened here, it's showing you here a short menu with all the types of mates that are applicable to these two faces that you selected, and it's already pre-selected the coincident type for you. If this is what you accept, if this is what you need, then you need to accept the result, and you will notice that the bracket has been moved such that its lower face is touching the top plane. Next, I need the front plane to pass through this, the long center line of this bracket. To do this, we have multiple ways. We can do the following. We can either measure the width of this bracket using the measure tool. We go to evaluate tab, measure, make sure to open this arrow, and I need to measure the distance between this face and that face. Simply click on both faces. And here's the width of the bracket. So the bracket has a width of 100 millimeters. So in this case, if I want the front plane to be at the center of this bracket, I can add a distance mate between one of the sides, right? One of the side faces, and the front plane, which is equal to half the width of the bracket. So let's try to do this and see what would happen. So I need a mate between, let's say, this face over here, and the front plane. But I don't want a coincident. I will pick a distance mate, and I need this distance to be 50 millimeters. You can see in the preview what happened here. So what happened is that it moved the bracket and it set a distance between the front plane and the face that I selected, which is the outer face of the bracket, at 50 millimeters as I entered. And it also rotated the bracket such that this face is parallel to the front plane. If you accept this, you will achieve the second result. So now our bracket is sitting on the top plane and it's centered around the front plane, and it only now has 1 degree of freedom, which is sliding along the front plane. Okay. Finally, I need to do the same thing with the right plane, but in the other direction, in the perpendicular direction. So I need the right plane to pass through the center of the bracket along its shorter side. So again, we can do the same approach, do the same thing, or we can do a slightly different approach. So the different approach relies on the planes of the bracket itself. And let me here stop for a second just to explain the difference between two types of planes in assemblies. So in the assembly workspace, as we start a blank new assembly file, you will automatically see these front, top, and right, and origin, okay, above any other parts. So these here, these represent the global coordinate system of the assembly, the whole assembly space, okay? But if you look at those individual components and open the arrow beside each of them, let's open all of them, you will see that each one of them has its own front, top, and right, and plane, and an origin. And similarly, the wheel has its own set of one front, top, right, and origin, and the bracket as well. So these represent the local coordinate system for each of the part files. Okay, and the best thing is that we can use the local coordinate system and the global coordinate system to apply mates to. That would help us orient or relocate our parts in the exact locations or orientations that we require. So let me show you an example of this. I will delete the mate that I just added between the front plane and the center of this bracket. Okay. By the way, any mate that you apply gets recorded under this folder here. So the last folder in the assembly design tree is called mates, and if you open it, you will see the list of all the mates that you applied. And the nice thing is that as you highlight any of those mates, just put the mouse cursor on any of them, it will highlight in the graphics preview. It will show you what are the involved entities. It will show you what is the mate between, what it is relating. Okay, so if you see, for example, the distance mate was between that orange side and the front plane that's highlighted in purple, and this coincident mate is between the top plane and the bottom plane, which is that bottom face, which is highlighted in orange, and so on. So let's select the distance mate and delete it. And I will even move the bracket out of the way, and I will add another mate between. Let's open the bracket first here. I'll open the arrow and let's see which plane. Okay, so the front plane, the front local plane from the bracket is passing through its center. So if I can align that local front plane with the global front plane, I will achieve the exact same result. How can I do that? Simply by selecting the front plane or open mates, Open the design tree here and select the front plane of the assembly and then the front plane of the bracket, but make sure that you are selecting the front plane of the bracket. In this case, it applied a coincident relation, which is exactly what we need. Now I will accept. Let's see if the right plane of the bracket also passes through the center of the bracket. So here's the bracket, the right plane. Oh, unfortunately it doesn't. So the bracket was designed such that the right plane is starting here at this side face. So we cannot apply the same coincident relation, otherwise it will not, the global right plane will not pass through the center. How can we resolve this? We can apply the similar distance mate like the one that we did a few minutes ago. So I will go again to evaluate, measure tool, and this time I'll measure the length of the bracket, the distance between these two faces, which is 150. So the distance mate that I will need to apply will be between this face and the right plane of the assembly. Make sure you select distance, and the distance will be 75 or 150 divided by 2. Accept, and you can see that the right plane is passing through the center of the bracket. Okay, now the bracket is fully defined. If you select the bracket, try to move it, it will tell you that the selected component is fully defined, it cannot be moved. And why is that? Because we applied the mates to remove all its degrees of freedom. So it's fixed to the top plane, fixed to the right plane, and fixed to the front plane, which prevents it from moving anywhere. Let me hide those planes and I'll bring those a little bit closer. Okay. The next step is assembling the wheel and the pin. So if I'm holding this in my hand and I'm trying to think of ways to assemble it together, the way that I would do it is that I will need to place or center this wheel between these two tabs in this distance, and then I would align the inner hole of the wheel with one of the holes of those tabs. Then I would take this pin and insert it through the first tab, then through the wheel, then through the second tab. Right, let's translate this into assembly mates. So I will go to mates and I will begin by aligning the inner hole of the wheel with the hole of the tab. And you can simply open the mates, just select the mate command and select the inner surface of the hole and the inner surface of any of those holes. And you will see that automatically it's suggesting a concentric relationship. So a concentric relation aligns the axes of two holes together. And this is exactly what we were after. So accept, and you will see now that the wheel can slide along the axis and it can spin. Next step, I need to place this wheel exactly centered here. So again, we have multiple ways to achieve this. The first way, we can use the evaluate and measure tool. In this case, we can measure the width of the wheel, for example, between this face, let's exit, and that face. Then measure the distance between the inner tab faces, this one and this one. Subtract the width of the wheel from the width of the bigger distance, divide by 2, and then you apply distance mate with the remaining value between one face of the wheel and one face of the tab. An easier way to do it again is using the planes if they are passing through the correct locations. So if you can find the local plane from the wheel that passes through its center, we can align it with one of the planes that's passing through the center of the bracket. So let's open the wheel, look at the local planes, and we see, yes, the right plane is passing through the center of the wheel. So we can mate the right plane of the wheel with the front plane of the assembly, which is already passing through the bracket. And in this case, you'll see that the wheel can only spin around itself, which is how it should move. in real life. Finally, we need to insert the pin in location, and this is similar to the alignment that we did between the wheel hole and the tab. So I'll simply select this face and I will mate it to one of the holes of the tab. It will be concentric, and accept. You will see that the pin can slide and can spin as well. So to stop it from sliding in or out, we need to make sure that the inner face of the head, or the bottom face of the pin head, is sitting on that face, which is a coincident mate. The last thing, you'll notice that now the pin can only spin, and I can make use of any of those flat faces on the head to make sure that it's fixed in place. And I will simply select this face, and I will select a horizontal face from the bracket, and automatically it will suggest a parallel mate. If you accept and try to move, you'll see that the pin is fully defined. So now the bracket is fully defined, the pin is fully defined, only the wheel, because it can spin in place. This is why the whole assembly is showing as underdefined. But again, it's unlike sketches. And in sketches, you must make sure that they are fully defined before you exit. For assemblies, it's not always required. Now, the next step is saving your assembly. So I'll call it assembly 2 as it shows up. I'll just save it here. Right. And the last important point that you also need to remember is saving assemblies. How can you save an assembly? What I did right now is saving an assembly. That's right. You don't see the asterisk here, or the star beside the name is disappeared. This means that the file is saved. But if you want to send or submit this as an assignment, you cannot take the assembly2 file and just upload it to Canvas. There's something important here that you need to know, is that if you submit only the assembly file to Canvas and I download it to open it on my computer for grading or reviewing, I will not be able to see your work. Unfortunately, it will open as a blank assembly on my computer. And the reason behind this is that SolidWorks only references the parts inside the assembly files. So in this case, whenever you want to submit an assembly for review, you need to include all the part files with your submission, which means that for this specific exercise, you need to submit 4 files. You need to submit the bracket, the wheel, the pin parts, plus the assembly file. Luckily, there's a way inside SolidWorks that can make this for you very easily and fast. So we need to use a tool that's called Pack and Go. And we can find it up here. If you touch the SolidWorks logo with the mouse, go to the File menu, and then go down the menu. You'll see here Pack and Go. Okay. As you select it, you will see the Pack and Go window. But to be able to see this window, you need first to save the assembly file. So it must be saved first. Then here it will show you the design tree. It starts with the assembly file name and then all the included parts. Make sure that they are all selected. Okay. Also, if we are going to use any parts from the toolbox or the design library, make sure to select here include toolbox components. Then you need to go down here to save as a zip file. And you click on the browse button to select the location where you want to save your file. So let's go here, for example, on the USB drive on this folder, and I will save it here. I will call it wheel assembly. Okay, wheel assembly.zip. And save. So now if you go and open the USB drive, new folder here, yeah, you see here in the assembly 2, this is the zipped file, compressed file. If you open it, you'll see the wheel, the pin, the bracket, and the assembly. This collects all the involved parts and it stores them into one compressed file. Okay, the last step that I need to show you here to complete this assembly is to add the 4 bolts in these 4 corner holes. And those bolts, because they are standard items, you can design them as individual parts, but it will be a waste of time because they are already available in the design library. The first thing you need to do, though, is to make sure that your toolbox is already loaded inside SolidWorks. To access the toolbox, you need to go to this vertical set of menus on the right edge of the screen. Look for the top 3rd one, which is called the design library. Click on it, and we are looking for the toolbox. As you click the toolbox, you should see a set of folders here. And if you open any of them, you should access all the internal components. If you don't see these, this means that the toolbox is not loaded inside your SolidWorks. So to load it, you need to go up here to the options button, select the arrow beside it, then go down to add-ins, and then find 2 lines, SolidWorks Toolbox Library. Make sure it's selected here and here, and the SolidWorks Toolbox Utilities. Also make sure it's selected here and here. Select OK, give it a second to load, and then go back to the design library toolbox. You should be able to see all the components. So for this specific exercise, I will go to bolts and screws, to the first type, hex head, and I will simply drag the first screw Okay, so let's do this again. We go to the design library, toolbox, and symmetric, bolts and screws, the first type. I will simply click and drag the first one, and I will just, without releasing the mouse button, I'll make sure to touch the inner surface of the hole and then touch the edge of the hole. What this does is that, as you noticed, the bolt adjusted its size according to the size of the hole, and it's showing me the size that it selected, which is the M10. M10 is a 10 millimeter diameter bolt. I will simply drag this arrow down to 40 millimeters to increase the length of the bolt, and I will click OK to accept. Then it will take me back to the insert component with the same bolt attached to the mouse. I will simply go again and touch the edge of the hole. You see this small icon beside the arrow. This is telling you that it's gonna place a concentric mate, then a coincident mate for each bolt. So click once to place this bolt. Again, I'll touch the edge to see the icon, then click to place. Similarly, click to place, then right click to exit. And this places the 4 bolts only using 4 clicks. And this concludes the assembly. I hope you find this useful. Please give it a try. Try to follow all the steps, and I'll see you in the next video.